For this last video in our chapter, I'm going to show examples of batteries, common ones that you use around the house and in everyday life, and how the setup of their chemical equations relates back to our diagram of a galvanic cell. So the first one to start with, by far the most important one, because, well, we used to use it every day, maybe not so much anymore, is our car battery. So you've probably heard this referred to as a lead battery. And that's because both reactions, so I have the anode and cathode listed down here, both half reactions in a car battery use lead. And one of the things to point out is that a lot of our reactions are much more complicated than the simple redox reactions we used. So real batteries have a lot more going on in them than the samples we have referred to. But the definitions and the key components stay the same. So every battery, remember our galvanic cells, the four key components, we had an anode and we had a cathode. We had a wire to allow the transfer of electrons, and we had a salt bridge to allow the transfer of ions. Well, the anode, of course, is always the loss of electrons. Cathode is always the gain of those electrons. And in a car battery, the way that this is set up is that there are plates or sheets of alternating anode and cathode in here. The transfer of electrons actually takes place directly between those sheets. So these metal plates are attached to all of those sheets, and that allows the electrons to transfer directly between them. Pardon my horrible graphics here. The other interesting part is that the salt bridge is dilute sulfuric acid. So you've heard about battery acid. If your battery ever leaks, that's battery acid that's coming out. That is sulfuric acid. And that sulfuric acid is the salt bridge. So rather than having a bridge that connects the two compartments like we drew in our galvanic cell, instead of a salt bridge here, these plates are all literally just sitting in a solution of sulfuric acid. And so each of the cells that we have in a car battery are only 2 volts. We put a total of 6 cells together, and that's how we get the 12 volts total. The next type of battery is generally called a dry cell or a Leclanche battery. Leclanche for the scientist who developed it. These are your typical double, AAA, your cylinder shapes. And so in here we have a zinc rod as our, this is the carbon rod that is serving as the cathode. And we have carbon in here because in this equation, we don't have anything that can serve as the actual electrode. So this is where we're using a neutral or an inert metal to serve as our electrode. Our anode is zinc, and that zinc is actually the canister on the outside. And so our cathode, our anode, the salt bridge is a paste made up of a bunch of different ionic substances in here. So not quite a liquid, but it more in a paste form. And the connection between the anode and the cathode takes place here at the very top where they come into contact. So a 9-volt battery. One of the things that I forgot to emphasize as we went through these videos is the voltage of a galvanic cell. So the voltage of any galvanic cell is limited by the half reactions that are used. So in other words, if I want to get 12 volts, like in a car battery, I have to put 6 of my cells together, 6 galvanic cells together. So a 9-volt battery, there is no combination of half reactions that will generate 9 volts. The only way to do that is to take 6 of our 1.5 dry cell batteries and connect them in series. So if you were to ever cut open a 9-volt battery, you would see 6 dry cell batteries connected in series, where we have positive connected to negative, so we can get that continuous voltage running through. And that's how we get our 9 volts. Our lithium-ion rechargeable battery. So I referred to this when we were talking about our electrolysis reactions. So when a rechargeable battery runs out of juice, you plug it into the charger, plug it into the wall. That essentially reverses the flow of the reaction. So in our lithium-ion rechargeable battery, we have our anode half reaction and our cathode half reaction. So when these run out of products, we plug everything into our recharger, and that forces each of these reactions to run in the reverse direction so that we generate our reactants again, so that when we plug our battery into our device, it can run again. So a couple of great things. A, these are rechargeable, right? So a longer half-life, less waste. Lithium is a fairly readily accessible element, and so there's right now a decent supply of it. It's also very lightweight, so batteries don't get too heavy with it, and it also produces quite a bit of potential. So the lithium ion cell itself can produce 3.7 volts. Another interesting battery design is the NiCad battery. This is a nickel cadmium battery. And the interesting thing about this one is the design of it. So it's what's called a jelly roll, or really rings of the negative electrode, your anode, and your positive electrode, with a separator in between, and that separator functions as the salt bridge. So similar in setup to our dry cell, but these are set up kind of in concentric sheets rather than as a whole rod in between. And of course, I love showing the setup of Tesla motors and their batteries. So for Tesla, if you've heard anything about them, the entire base of their car is a series of lithium-ion batteries. And in fact, in this model, I don't remember when I downloaded this picture, several years ago, but this model contains 7,104 lithium-ion batteries. So again, those rechargeable ones, but 7,000 batteries in the base of this. So they're so bottom heavy because the entire base is the battery. I have comparisons down here that we don't need to go into, but I do think it's very helpful. I don't know if I can bring this one around right now. I also like showing the setup that Tesla uses. So here is one of those lithium-ion batteries. And then you can see them in a little bit more detail. So all of these are in here. All of this is just lithium-ion batteries. And then, of course, they put the protective coating over it so that you have a little protection for your batteries. And so that is what the essentially innards of a Tesla motor car would look like. And that officially concludes our electrochemistry chapter.